Chapter 2, Section 2.7, Inverse Functions. Let's take a look at the objectives. We'll look at the definition of an inverse function. We'll also verify whether two given functions are inverses of each other. We'll show the procedure to, from an equation of a function, determine its inverse function. We'll determine whether the graph of a function has an inverse function, and if it does, we will graph that function. We'll also show the relationship of the graph of a function and its inverse on the same coordinate axes. Let's take a look at the definition of an inverse function. Definition seems somewhat complicated, but let's paraphrase. It simply says if you have two functions, let one function be named f and the other one g. If you do function composition, f compose g of x, and you simplify that resulting expression, and you end up with only the variable x, that is an indication, but not yet proof, that the two functions are inverses of one another. If you then compose the two functions in the opposite direction, g of f of x, simplify that resulting expression and end up with only the variable x, if both conditions apply, then f and g are inverses of one another. The statement down here gives us the notation for f inverse, and it comes with a small complication. F to the negative 1 power, that is not negative 1 power. This represents the notation for the inverse of a function. It says that if f has an inverse function, f inverse, and you were to compose them in either direction and simplify the resultant expression, you will end up with x. In other words, the statement here and here is the very same statement here, where g is now written in the notational style of f inverse. So first make a note here that f inverse of x does not mean 1 divided by f of x. That would be true if this negative 1 were an exponent, and although it looks like an exponent, it is not an exponent. If we wish it to be an exponent, we could write it this way. F of x in parentheses with a true negative 1 exponent outside would then mean the reciprocal of f of x. So you have to be careful with inverse function notation. The last statement here, the domain of the function f is equal to the range of the function f inverse and vice versa, simply means the following. If on the function f we have the ordered pair x comma y, then on the inverse function f inverse we have the ordered pair y comma x. In other words, the inputs and the outputs are interchanged. So the domain becomes the range and the range becomes the domain. This will be a very important idea later when we attempt to graph the inverse of a function. Let's find the inverse of a function and look at those steps. Show that each function is the inverse of the other. Okay, we have function f and we have function g. If they are inverses, then when we put the g of x function inside the f of x function, in other words, f compose g of x, f compose g of x, and simplify that resulting expression, we end up with the variable x. So let's take a look at that. Replace this x with the entire g of x function. So here it is. The x has been replaced by g of x. The 4's divide out, giving you then x plus 7 minus 7. The 7's add up to 0, giving you only the variable x. Now you must compose this in the opposite direction. You must then take g of f of x. In other words, g compose f of x. So now put the f of x function inside the g of x function. So where you see an x here in the g of x function, replace that with 4x minus 7. So instead of x plus 7 over 4, we here have f of x plus 7 over 4. The 7's add up to 0. The 4's divide out, leaving with x. Since the composition in both directions when simplified yielded the single variable x, we can then conclude that f and g are inverse functions. In other words, g is then named to be f inverse of x. Let's look at the steps to find an inverse function. The equation for the inverse of a function f can be found as follows. First, write y in place of f of x. So this is just rewriting the original function with y instead of using function notation. Second, since the domain becomes the range and the range becomes the domain, this means that you interchange the x and y, and then you solve for that expression for y. If that equation defines y as a single value, in other words, each x has one and only one y, then that resulting function will be the inverse. If by chance it does not and it's double valued, then the inverse will not be a function. This is best shown by an example. Let's move on to example 2. Given the function f of x equals 2x plus 7, let's find the inverse function. Step 1, very simple. Instead of writing the function using function notation, simply write y instead. So y equals 2x plus 7. Now, since the domain and range are interchanged, y becomes x and x becomes y. Now solve this resulting equation for y, and if it's single valued, then that function will be the inverse of the original. So we'll take this, move it down here. We'll then subtract 7 from both sides, and then divide by 2 to isolate the y. X minus 7 over 2 could be the inverse function. Let's see. If you input a value of x and subtract 7 and then divide by 2, you get one and only one y value. So it is single valued. So in other words, this new function y, as a result of this process, is the inverse function. And that's what we're saying down here in the last step. X minus 7 divided by 2 is now the inverse function, simply because the function x minus 7 over 2 is single valued. An example of when it wouldn't be single valued would be if this were a y squared. To get rid of the square, you would need to take a square root. Then you would get a plus or minus in front, and that would make y double valued. In other words, for each single value of x, you would end up with two values of y, and then that would not be an inverse function. If you're given the graph of a function, how do you know if it has an inverse function? Okay. A function f has an inverse, that is a function, if you can pass a horizontal line across the graph of the function and only intersect that graph one time. If you intersect it more than one time, then we can still find the inverse of that function, but the inverse will not be a function. And we'll show this a little bit more in detail when we do the problems. So this is a visual test that's fairly simple. We'll illustrate that by example 3. Which of the following graphs represent functions that have inverse functions? Okay, well, in black here is your function, looks like the absolute value. And in black here is a function that looks exponential. Now, each one of these is a function, the black graph here and the black graph here. Although, This function does not pass the horizontal line test, which means that each y does not have one and only one x. This y value here of 2 has two different values of x. So this is not one-to-one, meaning each x must have one y and each y must have one x. So this graph fails the horizontal line test, intersecting the graph at more than one place. So although we could make the inverse graph for this function, it would not be a function. Whereas in this picture here in B, this is a one-to-one function. It passes the vertical line test, so it is a function, and it also passes the horizontal line test, meaning that it crosses the graph of the function in only one spot. So we not only can make the inverse relation graph, that inverse graph will be the inverse function. Now we need to figure out how to draw the graph of an inverse function. Well, this is some help. It's good to know that the graph of the inverse function is a reflection, in other words, a mirror image of the graph of the original function about the line y equals x. It doesn't give you a recipe, a procedure, a set of steps to do it, so it's somewhat helpful. Let's take a look at example 4. Use the graph of the red function f to draw the graph of its inverse. Okay, first note that this is a function because it passes the vertical line test, meaning the vertical line intersects the graph only once. It also passes the horizontal line test, that any horizontal line can only cross the graph at most once. So this is one-to-one function, which means it does have an inverse. Okay, the inverse is represented here in the blue graph. And you can see that here is the line y equals x, and the blue graph is a reflection, a mirror image of the red graph about that slanted line there, as the next slide shows a little bit more clearly. Another way to say that it's a reflection or a mirror image is that the distance this point is away from the line y equal x is the same distance its inverse point will be on the other side of that line. So the distance from this point to the line y equal x is the same distance from there to here. But again, it doesn't give you a recipe for exactly how to do it. It's nice to visually see whether they are inverses, and that if they are reflections about the line y equal x. I'll give you more detailed procedure when we move to the examples.